we mentioned earlier during this lesson and discuss them a bit more before we move on, as they will be essential for what we discuss afterward. Low pressure shaft speed, or N1, is an indication of the fan rotational RPM speed. It's expressed as a percentage of a maximum RPM, in other words, the power that the engine is producing. The N1 instrument has reference bugs and red lines to display operating limits. N1 is a readout in white color under normal conditions and red color when the N1 operating limit has been exceeded. The EEC computes the maximum rated thrust for the engine during all phases of flight, and it shows as an orange color bug. The active flight phase is shown immediately above both engine N1 instruments. Exhaust gas temperature, or EGT, is an indication of the temperature of the gases that are escaping the turbines into the engine exhaust. It is of prime importance to monitor EGT, just like with N1. The EGT instrument also has a red line that displays the maximum takeoff EGT limit, an orange line that displays the maximum continuous EGT limit, and finally, a lower red line to display the EGT limit during startup. This last line disappears once the engine is started and is stable. Curiously, the EGT gauge also has an engine failure alert that is displayed in amber when the engine is running below its normal idle thrust, and the engine start lever is in the idle position. This alert stays unless the engine recovers or the start lever is moved to the cutoff position. In other words, fuel is isolated from that engine, or unless the engine fire warning switch is pulled. Aside from N1 and EGT, the total air temperature is displayed in degrees above the N1 indicators. Similarly to N1, the high pressure shaft speed, or N2, is an indication of high pressure rotational RPM speed. It is expressed as a percentage of a maximum RPM. N2 indicators have a red line to indicate operating limit, and the N2 indications turn red when this operating limit has been exceeded. There are also engine vibration indicators that display current engine vibration levels in white. The instrument has a high vibration limit marked by an amber line. When engine vibration exceeds this limit, the indication color scheme is reversed to draw the pilot's attention. Other secondary engine indications are the oil pressure, oil temperature, and oil quantity. Let's discuss the engine oil system on the 737NG. From small piston-powered aircraft to large turbofan jets, all aircraft use engine oil to lubricate and clean moving parts inside the engine and absorb some of the thermal energy that's released when the engine is running. Engine oil is almost as important as fuel. Without it, engines would overheat because of the intense metal-to-metal contact. The 737NG oil system is divided into three main areas: oil storage, oil distribution, oil indication. The oil storage system is in charge of making sure the oil is continuously supplied to both engines. There's an oil tank in the oil storage system that holds engine oil and allows oil level checks to be done. The engine oil tanks can each hold roughly 20 liters of oil. The oil distribution system is in charge of sending and receiving oil from the internal engine components. When oil is supplied, it's filtered to prevent contamination. After filtering, oil is also sent to the fuel-oil heat exchangers we discussed before, in order to make the oil temperature slightly cooler as it heats the fuel. Similarly to the fuel filtering system, oil also passes through a filter which may end up clogging with contamination. When this occurs, oil bypasses the filter and the oil filter bypass alert appears in the upper display unit. The oil indication system provides cockpit indications that monitor oil temperature, oil pressure, and oil quantity. These appear under the secondary engine indicators. Oil quantity indicators measure usable engine oil and display it as a percentage of the total quantity. When the oil quantity is 18 liters or higher, a full quantity indication is provided in the display units. A low quantity message appears when oil quantity decreases below 4 liters during at least 35 seconds. Also, the related quantity indicator's color inverts to alert the pilots of the oil shortage. Oil pressure indicators obviously measure and display oil pressure in PSI, pounds per square inch. The oil pressure indicators have 3 color bands: white, normal operating range; amber, caution range. Continuous operation in this range should be limited. The amber band is not displayed when N2 speeds are below 65%. Red, operating limit. The oil temperature indicators show engine oil temperature in degrees Celsius. It's measured using 2 sensors at different points that average out the readings and deliver one oil temperature indication. Oil temperature indicators also have color bands that have the same color meanings as the oil pressure indicators. If oil temperature stays in the amber color band for more than 45 minutes, the engine must be shut down, provided all other solutions have not been successful. To sum up, so far we've had a look at how the CFM56-7B engines on the B737 work, how they are fed fuel, how oil is cycled through them, and what kind of cockpit indications are associated throughout. All of our discussion has assumed that the engines are on and running normally. However, it's time to discuss how someone ignites and starts up these 2 giant turbofans. Starting up an engine safely, properly, quickly, and efficiently has always proven to be a challenge for most pilots. Even single-engine piston-powered aircraft can sometimes have very tricky startup procedures. It's important to know the reason why special considerations have to be taken in order to achieve safe and good startups, as well as maximize engine life. Us pilots like to constantly simplify things, so instead of going into excessive detail about components, we're going to look at the next few sections in a more procedurally focused way. We'll only be discussing normal startup procedures, as abnormal procedures are comprehensively discussed and evaluated elsewhere in our 737 NGX training. Essentially, there are 2 different types of normal startups: on ground and in flight. In the previous chapters, we saw that a series of compressors and turbines move shafts inside the engine and that the low pressure shaft, or N1, turned the engine fan. Now, how do the compressors and turbines move in the first place to achieve this desired fan movement? To do this, there are a couple of engine start switches, one for each engine, that have the following positions: ground, off, continuous, and flight. First, let's assume that everything else needed at this point for engine start is complete. That means that the air system is set up correctly, we have the power needed, fuel needed, and so forth. To get the related engine started, the pilot turns the engine start switch to the ground position. By doing this, the electronic engine control, EEC, and the APU receive engine start signals, and a start valve opens. When this valve opens, a Start Valve Open alert illuminates and power is supplied to the engine starter. The engine starter turns the engine N2 high-pressure shaft through the accessory gearbox we mentioned earlier. The engine starter manages to turn the N2 shaft by converting highly pressurized air into mechanical energy. This high-pressure compressed air is pneumatic power that is usable when the start valve opens. This air is provided by an engine start cart on the ground, an APU, or air pressure from another engine, assuming it's already running. As N2 revolutions per minute increase, all engine instruments must be monitored. However, special attention has to be given to N1, N2, EGT, fuel flow, and oil pressure. When N2 reaches 25% and the N1 has begun rotating, the pilots move the engine start lever from the cutoff position to the idle position. This action opens the fuel spar shutoff valve and allows fuel to start flowing into the engine fuel system towards the fuel nozzles in the combustion chamber of the related engine. Fuel ignition is also started when the start lever is placed in the idle position. If for any reason the engine doesn't seem to reach 25% N2, the engine start lever may still be moved to the idle position provided N2 is at least 20% and the N2 acceleration is lesser than 1% during 5 seconds. This condition is known as maximum motoring. When the engine is started and N2 reaches 56%, the engine start switches automatically move to the off position, and the start valve open light extinguishes. The ignition system supplies sparks to light the fuel in the combustion chambers. There are 2 ignition systems per engine, a right ignition system powered by the AC standby bus, and a left igniter powered by the related AC transfer bus. Only one igniter is necessary in order to perform an engine start, but this redundancy makes the start more efficient. There is an ignition selector switch that may select either ignition L, ignition R, or ignition both. AC buses are comprehensively discussed in the 737NG electric system lesson. From here, normal startup takes care of itself, and the pilots monitor for normal indications. Anything abnormal and quick shutdown can be performed, placing the engine start lever in cutoff and turning the ignition to off. But because we're only discussing a normal start, you'll see a final drop in N2 on the secondary indications. The ignition switch will automatically switch to the off position, which can be heard, and the engine should be running smooth and steady. The normal startup procedure on ground is fairly straightforward. However, as we mentioned before, we will not take into account the possibility of having hot starts, wet starts, and other types of abnormal conditions. The EEC has protection mechanisms where the engine start sequence is either detained or delayed when an abnormal start condition is detected. We've seen how engines are started on ground. Let's have a look at how they're started in flight in case an in-flight shutdown is imminent. Earlier on ground, highly pressurized air provided pneumatic power that was later converted to mechanical energy in order to turn the N2 shaft through the accessory gearbox. This high-pressure air is called bleed air, and we'll be discussing it in detail in the air systems lesson. However, we must know that during a ground start, bleed air is obtained from the APU. When the APU is inoperative, an external power unit may alternatively supply high-pressure compressed air.